lecture, we are going to start with the last section of this course. So basically, we'll be seeing some methods to solve the linear systems. Okay, so first we will revisit a few notions. So are you guys familiar with the norms? The notion of the norm? All right, so let's discuss it. Say if we have, so in the R, if we have say two real numbers, alpha and beta, right? So how do we denote the distance between the real numbers? How do we find the distance between any two real numbers? What's the notion used for that? So you have the notion of the modulus, right? So the distance between any two real numbers is nothing but mod alpha minus beta, right? And if you have to find, say, magnitude of any of the real number alpha, which is given by modulus of the alpha, right? So we have this notion of the modulus in the real number, right? So if we try to extend this to the, say, Rn or for the matrices, so that notion is going to be the norm. That is, if you want to talk about the distance between any two vectors or say any two matrices or say length of a vector, so how we will understand that, right? So for that, we require the notion of the norm. So let me give the definition. So I'm just going to discuss it for the vector and the matrices. Okay, so let's first see for the vectors, how did we understand this notion of the length? So what is a norm? It's a function, a vector norm on Rn. It is a function. Let's denote that function by these parallel lines. So it takes, so basically if you take any vector in Rn, the norm of that vector is going to be in 0. That is, it is going to fall into the positive real line. And it has the following properties. So this function should have the following properties to call it a vector norm. Excuse me. Now, what are the properties we seek for this function? So the first property which we want is that, so for the just for the notation convenience, I'm calling this norm itself, okay? But a function which will satisfy all these properties, that is called norm. But since I have to use this parallel line, so let me just call the norm itself. The norm of x has to be greater than or equal to 0 for all x is in Rn, right? And if you have that this is equal to 0, this is possible if and only if x is equal to 0, right? If norm of x is equal to 0, then x has to be 0, or other way around, if x is equal to 0, then norm of x will be 0. Right? This is the first property. Second property is that if we take any scalar alpha, and if we talk about the norm of alpha x, so this is the same as you multiply the norm of x by the mod of alpha. And this would hold for all x's in Rn and alpha in R. And third property we have is the triangle inequality. That is, if we talk about the sum of two vectors, the norm of that, this has to be less than or equal to norm of x plus norm of y. Okay, so this property is basically called the triangle inequality. Okay, so a function which we denote by this notion, so which satisfy all these three property, we call that as a norm on the Rn. So here note that I'm taking x is in Rn, so I will use this representation that x has a components as, this is just a notation, x1, x2 up to xn, and I'm taking a transpose of this, which means that when I say x is in Rn, I'm referring to the column vector having xi's as the components. So let's say some examples of the norm. So here we are talking about the norm of Rn. So norm on the Rn, we have various norms on the Rn first of all. So let's see some examples. So are you familiar with any norms on the Rn? Can you tell me? Excuse me. Euclidean norm? I think you'll be familiar. On R2 at least you'll be familiar with the various norms, right? So at least the Euclidean norm you might have used or come across at many places. So the first norm which we can define on Rn is Euclidean norm. And how does it, how do we define it? This is defined by, so let's see what is the notation I'm going to use first. So let's see. So this is denoted by, so I'm going to denote it by, I'll use the 2 in the subscript, okay, to denote the Euclidean norm. And it's defined as, so if I take x is in Rn and I'm going to talk about the Euclidean norm of this. So what it is, you take the components of these x, right? So we have the components as xi, square them, square their absolute value, but it's a square, so absolute value is the same as xi squared itself. Then sum it over, okay, and then take the square root. So this is what the Euclidean norm is. Okay, now let's see what other norms we can define on Rn. So the next norm we can define is the L infinity norm, which is also called the maximum norm. And it's denoted by, so I'm going to use these parallel lines, and in the subscript I'm going to use the infinity to denote the L infinity norm. So if we take x and if we talk about its L infinity norm, so how it is defined, you take the components of the x, take the absolute value, and take their maximum. So you will have the n absolute value. So this I is varying from 1 to n. Okay, so this is how we define the L infinity norm. So which means this is nothing but the maximum of mod x1, mod x2 up to mod xn. Okay, so let me give this recursive number. So this is 1, this is 2, and let's define L1 now. And this is denoted by, I'll use 1 in the subscript. So here, how do we define it? So we are talking about the x, the norm of one norm of x. So you take the components, take the absolute value and sum it over. Okay, this is called the L1 norm of the vector x. Okay, so note that I have just given the definition, right? So this is an exercise for you, that you verify that these three norms which we have defined here, that is a Euclidean norm, L infinity norm and L1 norm, all three of them, they satisfy the properties of this definition 1. That is, they actually define the norms. You have to verify that. Okay, so this is an exercise for you. Verify that. These which are defined in question 1, 2, and 3. They satisfy all the properties of definition 1. Okay, so you can easily verify that. Now let's talk about the matrix norm. So of course the matrix norm will also satisfy all these three properties, but in addition to that we will have a property in regard of the multiplication. So let's define it. So this is the definition 2. And note that I'm going to use this notation M and R. This is for the vector space of all n by n real matrices. Okay, so now let's see how do we understand the matrix norm. So a matrix norm, so it is again a function. It's denoted by these two parallel lines, and this is going to be a function. So let's write this is a function. Now this function is going to be, the domain is going to be M and R, and the range is going to be the positive real number. Okay? And this has the following properties. So the first property is that norm of any matrix has to be greater than or equal to 0. And if it is equal to 0, this is possible if and only if A is equal to 0. Okay, second property is that if we take any alpha as a real number and take any A in M and R, then if we talk about the norm of alpha into A, This is going to be mod alpha norm A. And third is the triangle inequality. That is, if we talk about the norm of A plus B, this has to be less than equal to norm of A plus norm of B. Now the fourth property which we have is with respect to the multiplication. So the first part is that if we take any two matrices A and B, then their product will satisfy this. And secondly, if we talk about the matrix and a vector, say X, and if you talk about its norm, so note that if you multiply a matrix with a vector, it is going to be a vector, right? So we have to talk about a vector norm here. So I have to differentiate the vector norm with the matrix norm. So let's take X is in Rn, and let's consider that that Rn is equipped with vector norm. We are denoting it by this. So I'm writing the V in the subscript to differentiate the vector norm from the matrix norm. Then, so if we talk about the product of A into X, this is going to be a vector. So basically we will have a vector norm here. So this is less than equal to the norm of A times the norm of vector X. Now again note that X is a vector, so this norm is here is going to be a vector norm. So this is for all X's in Rn and A is in Mn. Okay, so a function which satisfies all these properties on M, and it is defined on MNR, that is called the norm on MNR. Okay? And again, this is again I'm going to use the components of the matrix A as AIJs. So I'll write it in the component form in this way. Okay, so AIJ here is going to be the element of the matrix A, which is in the rth row and jth column. Okay. Now let's take some examples of the matrix norm. So the first norm is the column norm. And how it is defined. So so first of all, I'm summing it over. So note that I am a matrix, right? So I'm using the same notation here for the components, AIJs. So what I'll do, I'll sum the components over rows. So I is running from 1 to n. Okay. And then I'm going to take the maximum over columns. And this I'm denoting with a subscript 1 in the, so we'll have these parallel lines, and in the subscript I'm using 1 here. Okay. So as we have defined the Euclidean norm for the Rn, right? So we can define the Euclidean norm here as well. So So this is going to be that you take the components of the matrix, square them, sum them. So this summation is going to be over both I and j, and then take the square root. Okay, so this is how we are defining the Euclidean norm. And I'm going to denote it by these parallel lines and in the subscript 2. Okay, and next we can define. So here you can see that I have taken the summation over the rows and took the maximum over the columns, right? I can do the other way around. I can take the summation over all the columns and then take the maximum over all the rows. Right? So this also satisfies all the properties of the norm, and we are denoting it by these parallel lines and infinity in the subscript. This is called the row norm. Okay. Now there's one more norm which we will be using is the operator norm. And I think this is the one which you would have seen in the functional analysis course if you have already done. You guys have done the course functional analysis course?
No, ma'am.
Okay, I see. All right. So this norm, so these all the definitions, norms in a product you will learn in the functional analysis course, but I'm just introducing what we require for our purpose. Okay. We'll see in a more generalized setting when we will do the functional analysis course. So how do we define the operator norm for the matrices? So it is defined as the norm of A. This is going to be, so I'm going to take any vector Z. Okay, so I'm going to consider the product AZ. So AZ is a vector, right? So I'm going to use the vector norm for this. And then I'm going to divide it by the vector norm of the Z. And then I'm taking the supremum over all the Z which are not equal to 0. Okay. So you can observe that this is the same as if I write this as norm of AX such that X is in Rn and norm of X is equal to 1. So they both definitions are the same. So now again the exercise for you is that you have to verify that all these 4 definitions which we have seen here, they all define the norms. That is, you have to verify that they satisfy all the properties of this definition too. Okay, so this is an exercise for you. Verify that okay, so what I used for the Euclidean is 2. So for the Euclidean, either this notion is used or we also use the E in the subscript. So both notions are used for the Euclidean norm. So you have to verify that they all satisfy the properties of a matrix norm. Which are given in definition 2. Okay. So these notion of the norms I'll be mostly requiring when we will see the the convergence of the numerical methods, right? Because there we need to understand the distance, right? That is you have an approximation and then you have an exact solution, then you want to understand the distance between them. So there I will be requiring this notion of the norm. Okay, so let's review a few more things about the linear system of equations. So we are going to consider n linear equations and n unknowns. To consider the system of n linear equations and n unknowns. That is, I'm considering the system. So first equation is a11x1 plus a12x2, and the last entry in this equation is a1 and xn. This is equal to b1. The second equation is a21x1 plus a22x2 up to a2n xn. This is equal to b2. And the last equation in this system is an1x1 plus an2x2 plus ann xn. This equals bn. And let's call it 1. Okay. So this system, we can write it in the matrix form. So if we call this vector, so let's first write it down. So we'll have this x1, x2 up to xn. So the matrix here is going to be a11, a12. So this will correspond to the first row. That is the first equation. And the second equation is going to give rise the second row. So this is a21, a22 up to a2n. And likewise, the last row of this matrix is going to be an1, an2, ann. And this equals b1, b2 up to bn. Okay, that is, we can rewrite this system 1 in this matrix form. System 1 can be rewritten as this. So this is basically a matrix equation of the form Ax is equal to b. So if you call this as A, this as x, and this as b, so basically we have this matrix equation Ax equals b. So let's call it 2. So let's review one result which is concerning the solvability of this system. So let me state this as a theorem. So when does this system has a unique solution? What properties on the matrix A we see? I think you all will be familiar, right? You need the invertibility of the matrix A if you want to solve.
Determinant non-zero.
Yeah, so if you want to have a unique solution, you have to have I mean, this you have learned in the linear algebra course, right? The rank and the solutions, right? So you have learned those things in the linear algebra course. So, but here we are in the simple case because we have n by n system. So I just need the solvability of this. So I need the invertibility of the matrix A. So let A be a n by n matrix and B is an Rn. Then the following statements concerning the system of linear equations Ax equals b are equivalent. So basically, I'm going to state four. I think let's state it and then see how do we realize them. So the first statement is, as one of you said, the determinant of A is not equal to 0, right? So all the statements which I'm writing here, they're equivalent. Okay, that's what this theorem is telling. Now, for each right hand side, so for every right hand side vector, B, the system Ax is equal to B, this has a unique solution. Right? And it is equivalent to say that, in particular, if I consider Ax is equal to 0, that is, if we take B is equal to 0, then the only solution is going to be the trivial solution. Okay, so you can realize that how we are going to observe. So determinant of A is equal not equal to 0, this will clearly imply that this has a unique solution, and as a from 2 you can refer to the 3, and you can observe that how do you realize that 3 implies 1. So this you can just use the rank of the matrix, and what happens if you have only unique solution. So to realize that how the determinant will be non-zero when you have a unique solution of the Ax is equal to 0. Okay, so this so I'm not going to write down the proof here. You can just realize it by the concept which you have learned in the linear algebra. Okay, so what is our interest is numerical methods to solve this system, right? So we are interested in developing the numerical method to solve this system. Now, when we say numerical methods, so basically there are two kinds of methods to solve the linear system of equations. So the first method is, or the first class of method is the direct methods. So I'm categorizing them in two classes. First, the direct methods. Second, iterative methods. So what is the difference? So in the direct method, so though we are going to develop some algorithm to solve the system, but these methods gives you the exact solution, meaning there's no mathematical error. Okay, so let me just write this here. So direct methods so there is the exact solution of a linear system. Therefore, these methods do not have any mathematical error. So this is just a remark. So, but note that if you're going to use the computer, right? You use the computer to find, suppose you're solving the system Ax is equal to B, and say you're going to apply one of the direct method which we are going to discuss further, and you're finding the solution X using these methods. So though it does not have any mathematical error, but if you're using the computer to find it, there might be some round of error present in the solution. Okay, so this still might be the approximate value of the exact solution, in the sense that this might involve the approximate the round of errors, right? Because we know that the machine has its own limitations. So there's no mathematical error, but it will have some arithmetic error. That is a round of error if you're using computer to find the approximate solution. Now, what do we do in the iterative methods? So in the iterative methods, as you have seen, right? So we have seen the iterative methods. What does it yield? So it will be giving you a sequence of the iterates, that is a sequence of the approximate solutions, and which you expect that sequence will converge to the exact solution, right? So iterative methods, they generate a sequence of approximate solutions of the given linear system and this sequence is expected that it will converge to the exact solution. All right. So let's first focus on the direct methods. So in the direct methods, we are going to learn two methods, mainly two methods. So the first method we will see is the Gaussian elimination. And the second method which we will see is the LU factorization. Okay, and let me take one more assumption that I'm going to assume that the matrix A is invertible for until unless I'm specifying otherwise that it is not invertible. Till then, I'm working with this assumption that matrix A is invertible. So let me write this here. So just after the theorem. So this I'm taking assumption for the further discussion is that the coefficient matrix is invertible. So that I have a unique solution whenever I am talking about the system Ax is equal to B. Okay, so let's learn what is the algorithm for the Gaussian elimination. So I'm going to describe it first for the 3x3 system, and then we can easily generalize it to any general system of size n. So we are going to consider this 3x3 system. Consider the system of three linear equations in three variables. X1, X2, and X3. So I'll be sticking with the same notation. So coefficients are going to be Aij. So A11 X1 plus A12 X2 plus A13 X3. This is equal to B1. A21 X1 plus A22 X2 plus A23 X3. This equals B2. A31 X1 plus A32 X2 plus A33 X3. This equals B3. Let's call this as equation 1. So this is, I'm denoting it by E1, E2, and E3. Okay, and this complete system is so 2, 3. So this is 3. So what do we do in this algorithm? So the first step is that assuming that this entry is non-zero, we eliminate x1 from the second and third equation. Okay, that is the first step. And then what we will do, whatever is the resulting system we will get, from that I will eliminate x2 from the third equation. So this is the process we have to repeat. Okay, so let's write it down. So the first step is that we are going to eliminate x1 from second and third equation. And how do we do that? So I'm going to assume that A11 is not equal to 0. Okay, so we'll try to remove this assumption later. So first I'm assuming this, and then we'll see how to modify this method so that we can get rid of this assumption as well. So then I'm defining these multipliers M21. M21 I'm taking the ratio of A21 with the A11. And M31 I'm defining as the ratio of A31 with A11. Okay, and let's call this as. Now to eliminate x1 from E2, what I will do, I'll just multiply E1 by M21 and subtract from E2. So I'm going to subtract M21 times E1 from E2. Right? So that will eliminate x1 from the second equation. And now to eliminate x1 from the third equation, I will subtract M31 times E1 from the third equation. Okay, and what is the resulting system we get? So the system 3 will change to this following system. So we'll get rid of these two terms here. So the first equation will remain as it is, A11 x1 plus A12 x2 plus A13 x3. This equals B1, right? So this is as it is. Now I have eliminated x1 from the second equation. So I'm not going to have the coefficient of the x1 here. Rather, I'll have the coefficient of the x2. And this is going to change, right? It will not be the same as the A22 we have here. So I'm denoting it by A22 and this with this 2. This A23, 2x3, this equals B2. So all the coefficients which have changed, I'm denoting them in the superscript with this bracket 2. Okay, and let's call this 5. Now, what are these coefficients? The new coefficients which I'm using here. So Aij 2 is what it is going to be. So what I'm doing, I'm just multiplying by these multipliers M21 and M31 and then subtracting to the corresponding equation. So they are going to be Aij minus Mi1, and note that this I'm writing for I is equal to 2 and Ij equal to 2 and 3. So this is going to be Mi1 times A1j. Ij equals 2 and 3. And B will change to, so Bk 2 is going to be Bk minus Mk1 B1. Okay, so these are the new coefficients which we will have in this reduced system. Now, what is the next step? So we have eliminated x1 in the first step. The next step is that you assume that this coefficient is non-zero, and then we are going to eliminate x2 from the third equation. So step 2 is eliminate x2 from, so let me again call it E1, this is E2, and this is E3. So eliminate x2 from E3 in system 5. So for that, we assume that with A22, 2, this is not equal to 0. And define the multiplier M32 as the ratio of A32 with the A22. Okay, then how will I eliminate this x2 from the third equation? I'll multiply E2 by M32 and then subtract from the E3. Subtract M32 times E2 from E3. So this will give us this new system. So the first equation will remain as it is. Second equation will also remain as it is because we are not doing anything there. What will change is the third equation. So I will not have the coefficient of the x2. Only term which will be left is the coefficient of x3, which is going to be A33. So this is a new coefficient. So I'm changing the superscript here. times x3, this is equal to b3. Now what is this coefficient here? This is A332 minus M32, and then we are multiplying with the A23. Okay, and B33 is B32 minus M32 multiplied by B2. Right? So this is how we get a reduced system. Okay, so you can see that if you try to observe that we started with the form Ax is equal to B, right? If you try to see the coefficient matrix here, this is like a, if you call that as a matrix A, so this is like Ax is equal to B, where A is this coefficient matrix Aij. Now what this reduced system says, if you try to write it down, let's give it a equation number. So this is 5, 6, and this is 7. So the coefficient matrix of system 7 is, so just write it down. What is the system we have there? So what is this matrix? This is A11, A12, A13, A22, A23, 0, 0, 0, 833, 3. Right? So you can realize the structure of this matrix. This is an upper triangular matrix. Okay, so the coefficient matrix of system 7 is an upper triangular matrix. So if we set this matrix as U, then basically I can write down the system as Ux is equal to G, okay, where G is this vector B1, B2, B3 with these correct indices. Okay. Now note that solving this system is very easy, because if you you just start solving from the last equation, that is which we call the back substitution. You first solve the last equation for x3, right? Once you have found x3, you solve for x2 from the second last equation, and then finally you solve for x1 from the first equation. This is step 3 that we use back substitution. In this system in 7, to solve successively for x3 and then x2 and then x1. So what do we get? So if you solve the last equation, assuming that 833, this is not equal to 0. Okay, so we'll get x3 from there, and then you get x2. So we assume that A3, 3, this is not equal to 0. So then we get x3 as, what do we have? B33 divided by this component. And then x2, you can solve it from the second last equation. So this is going to be B22 minus, so we will have A22 going that side. So we'll have A23 2 times x3 divided by A2. Okay, and then from the first equation we can find x1. So this will be B1 minus A12 x2 minus A13 x3 divided by A1. Okay, so this is basically the algorithm for the Gauss elimination. This is how it works. Now, there's one more observation we can make here, that we have been finding these these multipliers here, right? M21, M31, and M32. So if I form a matrix using these multipliers, so I'm keeping the diagonal of this matrix to be 1. The upper diagonal is 0. And the lower diagonal, I'm using the multiplier. So this is M21, M31, M32. There was a reason why I was naming them with these indices MIJs. Okay, that I wanted to form this matrix. So let's call this L. So we have this matrix U here in 8, and let's call this 9. So if you just multiply these two matrices, that is, if you consider L into U, you can observe that you will get back A. Okay, so this is just an observation you can make. So here M21, M31, and M32, they are defined in these equations, which are 4 and 6. Okay, so this is for you to verify. You just simply multiply these two matrices, L and U, and you will get back A. Okay, so this is how we have to apply the Gauss elimination. So is the algorithm clear, that what do we do here? Then we can write down the general case as well. Any doubts here? Anybody? Are you guys with me?
Yes, ma'am, no doubt.
Yes, ma'am.
Oh, all right. I think some of you have to respond, because otherwise I feel that whether you guys are hearing me or not. So, all right. So let's just simply extend it for any general n if the idea is clear. So for general case, so let's assume that we have the n by n system. And I'm denoting it by, so we have Ax is equal to B, and just for the notational convenience, so I'm denoting it by A1 and B1. Okay, so for uniformity in the notation, so we're denoting the original system by this. That is, my coefficient matrix here is going to be having the component as Aij with the superscript as 1. So these, we are going to have the equations as this. So this times xn, this equals bn1. Okay, and let's call this as E1, E2, and the last equation is En. And this is the equation number 10, system number 10. So what will be the first step? We just eliminate x1 from E2 up to En, right? And we'll get a resulting system. And from the resulting system, we eliminate x2 from E3 to En, right? So this is the process we have to repeat. So let me write a general step K, that what we will do in the step K. So for K equals 1, 2 up to n minus 1, we carry out the following elimination step. So in the step K, we will be eliminating xk from the equation number k plus 1 to n, right? So let's write it down. So we eliminate xk from ek plus 1 to en, not the same ek plus 1 to en. So these ek plus 1 to en are going to be in the system which we will get at the step k minus 1. Okay, so let's write it down. What is the system we are going to have at the step k minus 1? So the result of resulting system of the preceding steps which are 1 to k minus 1, this will yield the following system. So first equation will remain as it is. Right? From the second equation, since I'm writing the step, the system which we will have at the step k minus 1, so note that I'm not going to have this x2 from the second equation because that I would have already eliminated. So this will be a22 to x2 up to a2n to xn, this equals b2 2, right? And this will continue up to I will reach this step akk kxk up to akn kxn, this equals bk2. And now this will continue. The last equation I'm going to have it as ank kxk plus ann kxn, this equals bnk. Okay, so this is E1, E2, this is EK, and this is En. Okay, and let's call this as 11. So what we have to do, we have to eliminate xk, so we have it from ek to en. So I'm going to eliminate this xk from ek plus 1 to en. So for that, what I have to assume? So I'm going to assume that akk, this coefficient here, is not equal to 0. And then I'm going to define the multipliers as the ratio of this akk to the coefficient of each of the xk's in the rows which are below the row ek, right? So I'm going to define mik as aikk divided by ak, everything with the superscript k. And this is going to happen from the row k plus 1 to n. So once we have found the multipliers, we are going to subtract mik times ek from ei for I equals for the equations k plus 1 to n. Okay, so basically you will eliminate xk from xk plus 1 to, so from the equation number k plus 1 to the equation number up to the equation number n, right? So let's say the resulting system is this new system. Okay, let me directly write down the coefficients because every time I'm not going to write the system. So the new coefficients are going to be so what coefficients we will get up to the ek, nothing is going to change. From ek plus 1 to en, the coefficients are going to change. So we are going to call them the next index, which is k plus 1. This is going to be aij k minus mik times akj k. And I and j are varying from k plus 1 to n. And bi k plus 1 are going to be bik minus mik times bk, where I is varying from k plus 1 up to n. Okay, so if you continue to repeat this process, so this is the step k, and k is varying from 1 to n minus 1, right? So at the n minus 1 of the step, what we will get? So you just complete the step n minus 1, the result is going to be an upper triangular matrix. And let's write down that what is the final matrix which we are going to get after the step n minus 1. So when the step n minus 1 is completed, the linear system will be in upper triangular form, which we are denoting it by. So I'm using the same notation. We used U before and G for the right hand side. Say Ux is equal to G. So if I call the matrix U as Uij's, so that is I'm going to have the equations as U11 X1. So you have to have the Uij's in 0. So all the non-zero entries, I'm calling it as Uij's. So let's write it down explicitly. U1 and Xn, this is equal to G1. And in the second row, I will start from the U2 to X2 up to U2n Xn, this is equal to G2. Likewise, the last equation is going to be UN and xn, this equals gn, right? And how does these ui's and gi's relate to the ai's and aij's and bij's? So uij's are going to be aij's at the ith step, and GIs are going to be BI I. Okay, so if we give this as equation number, so these are 13 and these are 14. So the last step is going to be that we are going to solve this system 14 using back substitution. That is, we'll start solving from the last equation and then we go in the upward direction. So the last step, which is step n, this is going to be that solve system 14 using back substitution. So that will give you the coefficients xn minus 1 up to x1 successively. Okay, so what those coefficients are going to be, xn is going to be simply gn divided by unn. So I'm going to write down in terms of these uij itself, and xi's are going to be for any I from n minus 1 up to n, you can compute it by this. So this is going to be gi minus summation uij xj, and j is varying from I plus 1 to n divided by uin. Okay, so this is the algorithm for the Gauss elimination for n by n system. Okay, and as before, if you just form the matrix of the multipliers, that is, if you define the lower triangular matrix L by so I'm going to take the diagonal to be 1, that is all the entries in the diagonal is going to be 1. And then upper diagonal is going to be 0. And the below diagonals are formed by the multipliers. So M21. And so we have all the multipliers. So you can just keep them so we have already given indices to the multipliers, right? So you can just put them in the right places. Where these MIKs are defined. I think we give the equation number. So this is 12. Right? So we have formed this matrix. So now you can verify that if you multiply L and U, you will get back A. Right? So U is the upper triangular matrix which is given by 14. Okay, so U is this upper triangular matrix. All right, so I think you guys might already be familiar with this algorithm. So is it clear? Any doubts so far?
No,
Okay, let's quickly take one example and try to work it out. So we have to solve this linear system, x1 plus 2x2 plus x3, this is equal to 0. 2x1 plus 2x2 plus 3x3, this is equal to 3. And then minus x1 minus 3x2, this is equal to 2. So I can write this in this form, Ax is equal to B, where the matrix A is 1, 2, minus 1, 2, 2, minus 3, 1, 3, 0, and X is the vector x1, x2, x3, and B is the vector 0, 3, 2. So note that when we were applying the this Gauss elimination, you can see that the role of the xi's are really not getting played here, right? So you see x is remaining the same vector till the end. Only the coefficients of the matrix A and the right hand side vector is changing, right? So I can very well work with the augmented matrix, right? I can just write these variables x1, x2, x3 in the last step itself. Okay, so since these unknowns x1, x2, and x3, they enters into the Gauss elimination algorithm, in the final step only, we can, so basically we are going to use the augmented matrix to represent this system. So I'm using this notion for the augmented matrix. So I'm separating them by this this line here, the matrix A and the right hand side vector B. Okay, so this basically signifies that we are solving Ax is equal to B. So what is this? So we already have this matrix whose rows are A1, 2, 1, 2, 2, 3, minus 1, minus 3, 0. And this vector is 0, 3, 2. So now the first step is that we define the multiplier M21 and M31. So note that A11 is 1. So M21 is simply going to be 2 divided by 1, which is 2. And M31 is minus 1 divided by 1, which is minus 1. Right? So then you basically apply. So this is your first row, second row, and third row. Right? So we are going to perform E2 minus M21 times E1, and then E3 minus M31 times E1, right? So if you perform this, we'll get this new matrix. So where first row will remain as it is. In the second row, of course, these two entries are going to be 0. Now what will be the other entries? So we can simply do the calculations here. So this is 2 minus 4. So we'll get minus 2, and then minus 3 plus 2. So minus 1. And then 3. So here we have 3 and then minus 2. So we'll get 1. And 0 minus minus 1. So this is also going to be 1. And this will change to, so since this entry is 0, so this will remain as 3 to itself. So now we are going to eliminate x2 variable. That is, I'm going to eliminate this variable here. I'm going to make this 0. So for that, I define M32 as this coefficient divided by the -2. So this will be 1/2. And if I call these E1, E2, E3 again, so now I'm going to perform E3 minus M32 times E2. So this will reduce the matrix to first row remain as it is, second row remain as it is. For the last row, this will be 0, this is 0. Now this will reduce to 1 minus, so this 1/2, so this will be 1/2. And this is going to be 2 minus 3/2, so this is also 1/2. Okay, so note that we have the coefficient matrix has become upper triangular here. So if we denote this as U and G, so we can basically solve Ux is equal to G. So what we will get? So see the last equation. So last equation is 1/2 x3 equals x3. Sorry, 1/2. So this will imply that x3 is 1. And then from the second last equation, we have that minus 2x2 is going to be 3 minus x3. So this is going to be x3 minus 3 divided by 2, which is -1. And then likewise, from the first equation, we'll get x1 as minus 2x2 minus x3, which is 1. Okay. So this basically gives the solution of this system. And you can also note that we have this matrix U as 1, 2, 1, 0, minus 2, 1, 0, 0, 1/2. And you can form this lower triangular matrix using these coefficients. So we have got this 2 minus 1 and 1/2. So this is going to be 1, 0, 0, 2, 1, 0. So diagonal I'm keeping 1. Okay, and this is M21, and then M31 is -1, and M32 is 1/2. Okay, and you simply multiply L and U, you can verify that this is the same matrix A. And of course, this also gives you that you can easily find the determinant of this matrix. Now, determinant of L is 1 because the diagonal entries are 1, and determinant of U is nothing but the product of the diagonal entries. So, which is 1 into -2 into 1/2, which is 1. Okay, and which is non-zero.
-1.
So, I think this is all today. Yeah.
Determinant of U equal to -1.
Determinant of U is 1 into -2 into 1/2. Yes, this is -1. Thank you. Okay, and determinant of L is simply 1 because this is how we are constructing the L, that diagonal entries are 1. Okay, so we'll stop here. In the next class, what we will try to do, we have been keeping this assumption that we are assuming that some of the coefficients are non-zero, right? So for example, we consider that AKK is not equal to 0. Right? So we'll try to remove these assumptions and try to modify this Gaussian algorithm. Okay, so that we will do in the next class. All right, so I'm ending the meeting here.